What if humans evolved in a world with no gravity at all? How would our bodies transform? The human organism is a product of millions of years of evolution in a world dominated by gravity. Every system, from the skeletal architecture to the circulatory patterns, neuromuscular coordination, and sensory calibration, reflects persistent gravitational loading. In a hypothetical environment where humans experience permanent zero gravity over evolutionary timescales, the primary selective pressures acting on the organism undergo a profound realignment. This part of the hypothesis investigates the foundational biological pressures that would drive evolutionary redesign, outlining the fundamental forces shaping a zero-gravity human lineage. In a microgravity environment, the absence of gravitational pull disrupts the mechanics of posture, locomotion, and fluid dynamics within the body. Human physiology is optimized for standing, walking, and resisting compressive forces imposed on bones and joints. When gravity is removed as an environmental constraint, the organism experiences systemic imbalances. Short-term adaptations observed in astronauts' bone demineralization, fluid shifts toward the head, and muscle atrophy offer a preliminary framework. But these represent acute physiological responses, not stable evolutionary pathways. Evolution requires heritable variation interacted with long-term environmental pressures. Over many generations, these pressures would push the human body toward structural, metabolic, and sensory recalibration. The most immediate selective pressure arises from the inefficiency of locomotion in zero gravity. Without gravity, walking is obsolete. Propulsion depends on pushing against surfaces or manipulating body mass to generate directional motion. In early generations, individuals with proportionally stronger upper body musculature may experience functional advantages, achieving more controlled and efficient movement through free-floating environments. Over long evolutionary periods, these advantages translate into differential reproductive success, gradually steering the population toward increased arm strength, enhanced shoulder mobility, and redistribution of muscle mass away from the lower limbs. Because inefficiency wastes oxygen and energy-critical resources in enclosed habitats, selection would favor individuals who maneuver effectively with minimal metabolic expenditure. Alongside locomotion, the skeletal system faces a major selective realignment. Gravity-dependent bone remodeling processes cease, and high-density bones become metabolically expensive liabilities. Osteoblast and osteoclast activity patterns would shift, gradually trending toward lighter skeletal structures. Although short-term astronauts experience harmful bone loss, evolution would eventually establish a new set point where bone density stabilizes at lower levels without compromising structural integrity. Described the overarching evolutionary pressures, Part 2 focuses on the specific structural transformations that emerge once those pressures begin shaping anatomy at the population level. The most visible and rapid transformation occurs in the lower limbs. Legs become functionally redundant when locomotion no longer relies on walking or balancing against gravity. Evolution does not remove legs entirely. Vestigial structures persist for long periods, but their mass, length, and musculature decrease substantially. Reduced femoral diameter, lighter tibial shafts, and a narrower pelvis reflect a shift away from load-bearing requirements. The pelvis, in particular, transitions from a broad, supportive basin into a compact, streamlined structure, optimized for minimal metabolic cost rather than structural stability. In contrast, the upper limbs undergo significant enhancement. Arms become primary tools of propulsion, steering, and environmental interaction. Natural selection favors longer humeri and more flexible shoulder joints, enabling greater reach and rotational control. Individuals with enhanced grip strength, improved fine motor coordination, and broader upper thoracic musculature maneuver more effectively, conserve energy, and avoid injury, all of which translate into reproductive advantage. Over many generations, this results in an upper body dominant morphology with proportions reminiscent of arboreal primates but adapted for three-dimensional movement rather than climbing. The spinal column evolves toward increased flexibility and reduced compressive robustness. In the absence of vertical loading, vertebrae require less dense cortical bone, and intervertebral discs adapt to support multi-directional bending. A more serpentine spine enhances agility, allowing humans to twist and pivot fluidly in midair. This structural redesign also reduces the risk of injury from sudden orientation changes, a common hazard in microgravity. Cranial evolution trends toward enhanced sensory processing. With three-dimensional spatial navigation becoming essential, individuals who exhibit larger or more efficient vestibular systems achieve superior orientation stability. The semicircular canals may expand or change curvature to improve sensitivity to angular acceleration. Eye placement and field of view broaden subtly to support omnidirectional awareness, while neural circuits integrating visual, vestibular, and proprioceptive signals become increasingly sophisticated. The rib cage and respiratory apparatus adapt as well. Without gravitational tension influencing thoracic mechanics, the rib cage becomes lighter and more flexible. Diaphragmatic function shifts to accommodate spherical air circulation patterns common in enclosed habitats. As human populations persist for generations in a zero-gravity environment, evolutionary forces begin reshaping the nervous system and sensory frameworks at a fundamental level. The brain and organ already optimized for terrestrial orientation must recalibrate to support a world without up, down, or linear gait-based motion. Over time, individuals with certain neural predispositions gain substantial survival advantages, and these traits proliferate through the population. The most influential transformation emerges in the vestibular system, which normally relies on gravity to detect orientation and acceleration. In microgravity, this system produces misleading signals, causing spatial disorientation, nausea, and impaired motor coordination. Evolution resolves this by favoring individuals whose vestibular apparatus exhibits reduced reliance on gravitational cues and increased sensitivity to rotational and linear motion alone. The semicircular canals gradually enlarge or alter their curvature, enhancing detection of movement in all three axes, while the otolith organs, traditionally gravity-responsive, shift towards sensing dynamic internal fluid displacement instead. Over many generations, these changes translate into highly stable 3D orientation capabilities. Complementing this evolution, the visual system undergoes significant refinement. Because visual cues replace gravity as the dominant reference for spatial awareness, selection favors wider peripheral vision, increased retinal sensitivity, and enhanced depth perception. Neural processing centers in the occipital and parietal lobes expand to integrate continuous streams of visual and proprioceptive data. This results in a brain capable of building rapid spatial maps of complex environments, supporting agile maneuvering in free-floating habitats. Meanwhile, proprioception becomes more sophisticated. In gravity-rich environments, proprioceptive feedback relies heavily on load-bearing sensations from muscles and joints. Zero gravity eliminates these cues, forcing reliance on internal positional awareness alone. Individuals with naturally heightened proprioceptive acuity, more responsive muscle spindle fibers, more sensitive joint receptors, and faster afferent nerve conduction gain a competitive advantage. Over time, neural circuits handling full-body positional awareness expand, enabling precise movement control without the stabilizing anchor of gravity. Cognitive evolution also progresses. Zero-gravity environments demand complex problem-solving, rapid adaptation to disorienting situations, and heightened situational awareness. Over generations, selection gradually increases neural efficiency in the prefrontal cortex, improving working memory, predictive modeling, and rapid decision-making. Individuals exhibiting calmness under sensory ambiguity. Over extended evolutionary time scales, the most profound pressures shaping a zero-gravity human lineage concentrate around reproduction, metabolism, and genetic drift. These processes ultimately define whether zero-gravity humans remain a variant of Homo sapiens or diverge into a distinct species adapted to permanent microgravity. The reproductive system undergoes the strongest directional selection. Gravity influences embryo positioning, uterine blood flow, and birthing mechanics. Without these forces, early pregnancies are highly unstable. Individuals possessing genetic traits that improve implantation, stability of embryonic orientation, and placental attachment gain decisive reproductive advantages. This drives evolutionary shifts in uterine musculature, hormonal gradients, and pelvic architecture, favoring a narrower, more cylindrical pelvic structure and a uterus optimized for anchoring embryos in three-dimensional space. As birth canals lose their terrestrial load-bearing function, childbirth transitions toward a process relying more on coordinated contraction patterns than gravitational assistance. Over many generations, these changes accumulate into a reproductive physiology fundamentally distinct from Earth-adapted humans. Metabolism also evolves under new constraints. Microgravity environments, whether orbital colonies or deep space habitats, typically operate under limited resource availability. Selection strongly favors energy-efficient phenotypes. Individuals with lower basal metabolic rates, superior mitochondrial performance, and reduced oxygen consumption gain a survival advantage. Muscle mass trends downward in the lower body and shifts toward a more balanced distribution around the torso and arms. This allows for efficient propulsion without the resource burden of maintaining unused musculature. Over time, metabolic pathways recalibrate to prioritize endurance and cognitive performance over strength or terrestrial locomotion. The human body becomes a low-power, high-efficiency biological system adapted to enclosed ecological loops. At the molecular level, radiation tolerance becomes a significant evolutionary factor. Even shielded habitats expose residents to elevated radiation levels compared to Earth. Mutations damaging reproductive or neurological function are strongly selected against, while traits supporting DNA repair, antioxidant production, and cellular resilience proliferate. These changes produce a lineage increasingly resistant to radiation-induced diseases, including certain cancers. As these anatomical, physiological, and molecular changes accumulate, a gradual speciation process becomes inevitable. Genetic drift accelerates in isolated spaceborne populations, especially when small founder groups inhabit separate colonies.